Hi. Have you heard of the Theorem of Pythagoras? I'm sure you have. Let's see what it looks like. We have a triangle with sides A, B and C, and if we draw squares on each side of the triangle, we find that the sum of the area of the two smaller squares, in other words A squared plus B squared, is the same as the area of the larger square, C squared. And we can write that as a formula. A squared plus B squared equals C squared. But can we prove that that is always true for a right-angled triangle? There are many proofs that have been given. Here's a particularly simple one. Let's suppose we start with a large square and it's been subdivided into different shapes. One of the shapes is a blue square with area A. Then we have a square on the bottom right with area B. And then we have four green triangles, each the same size. And each one we can refer to as having area T. Now the total area, which we will call area 1, is the sum of all those little areas. In other words, area A plus area B plus the area of the four triangles. Now, what's area A? Well, the side length for square A is A, little a. So the area of a square is length times width, which is A times A, which is A squared. What about area B? That has side length little b, so the area would be B times B, which is B squared. And we add to that the area of the four triangles. Well, we don't know about the length and the side. We don't need to at this stage, as you'll see in a little while. So let's just call them four triangles, the area of four triangles. So that gives us the total area of the large square. Now, we will start with the large square again, but this time we will divide it differently, something like that. Can you see what's happened? We still have our four small green triangles and another square rotated. Not the same size as area A in the first shape, and that's why we've called this one area C rather than area A. But what do we know? Well, we know that the total area has to be the same as the total area of shape 1, because they are the same size. So let's see what the total area of that second shape is. It's made up of, as we said, the four triangles and the square. So it's made up of area C plus the four triangles. Area C is a square of side length C. So the area is C times C, which is C squared. And of course the area of the four triangles, just as in the previous shape, we can write it as 4t. So the total area 2 is going to be given by C squared plus 4t. Okay, we're almost there. What do we know? We know that the total area 1 has to be the same as total area 2 because they are the same large shape but divided differently. It's like slicing a pizza, isn't it? Whether you slice it up into 4 pieces or 8 pieces, the shape of the pizza remains the same. Okay, let's write that down. Total area 1 must be the same as total area 2. There it is. And we can write down what we know about each of those areas, area 1 and area 2, like that. That's an equation now, isn't it? Can you see anything that would cancel? Yep. 4t is on both the left side and the right side, so effectively they cancel out. And we can show that by subtracting 4t from both sides. Doing that, this is what we're left with. And isn't that our formula for Pythagoras' theorem? Of course it is. This is a very simple, neat proof that you can easily reproduce if you have to. And it's good to know where it comes from. I encourage you, though, to look at other different proofs just to see how many different ways there actually are to providing proof for Pythagoras' theorem. Till next time, bye-bye.